So let's start. Что-то его не так много, ну ладно. Будем агрессивно пользоваться тогда. Right. So last time we started talking about vector fields on a supermanifold, and so let's recall the definition and then proceed. So definition was the following. Okay, so my supermanifold is X, structure sheaf is O, so this is supermanifold, and well, I'm saying that vector field on open subspace U in X is really just a bunch of superderivations. So it's a collection of, at least that's how we defined it last time. From where? From well, O of V to itself. So for any V in U open, well, such that it commutes with restrictions. So such that they commute with restrictions. And so Sergey noted that maybe we can just say it's superderivations from OU to O of U, right? That was your offer. I'm still not quite sure because, well, this gives us restrictions to all the open, like automatically, this definition, right? Because like, well, I just define, well, if I have vector field, I would like to define it on subset, an open subset, right? So how do I, so I'm not sure how do I define this if I just say it's a superderivation on O of U. Ну да. Ну, то есть здесь я как бы руками это ввожу.
Ну, там стандартно это делается, так что у нас есть сечение на какого-то множества.
Да.
Мы хотим идентифицировать его в какой-то точке, но вот если бы это была функция, мы могли в какой-то точке брать значение. Мы что делаем? В окрестности, ну, умножаем на которая в окрестности этой точки и дальше у нас, это уже будет глобальное сечение.
Ну да, ну правильно, это тут что такое касательное пространство, здесь это чуть-чуть по-другому. То есть на самом... Ну да, но они есть как бы, но это не дает, это как бы вот только первая компонента, в которой коэффициент. Ну да, они не вписываются полностью, да. Ну, у нас будет вот сейчас касательные пространства, вот. Ну и мы там действительно теряем какое-то количество информации. All right. So this is it, and we also saw a couple of examples which are actually, you know, we will see in a minute. This will form a basis. So we have, well, if we just fix consider R, Mn, right? Yeah, by the way, so okay, I decided to get rid of parentheses since it's kind of now artificial. So if you're okay with that, so this is really a super manifold, right? This Rm and then C infinity Mn, right? Since we don't have too much of super vector, well, we don't use this too much as a super vector space. Okay, let's get rid of this. This is one thing. Another thing is that maybe let me introduce a handy notation. If I have U inside Rm, I can introduce a super manifold UMN, which is just a restriction of this to U. All right. So this is just U, well, C infinity Mn U. That was our notation for restrictions. And well, so I would like to see what are the vector fields on any UMN. And we have just usual derivation d over dxi, right? Which just takes f I theta I and just differentiates each coefficient. So I also have sum here. So this will be just d over dxi fi sum over I theta I. And we have also well derivations with respect to thetas, which are also so-called left derivations, and they are defined as follows. So if I have something like some element g in C infinity Mn of U, such that theta I g is not 0, so it does not contain theta I, then this is 0, and d over d theta I is times theta ig is g. Well, it's clear you pull theta I if you find it to the left and then erase it. So then we have proposition. That this form a basis of well, let me so really d, so let me call it somehow beta, which is d over dx 1 blah 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 d over dxm, d over d theta 1 d over d theta m. So it's a basis of derivations of C infinity Mn of U over C infinity, of course, Mn of U. And well, this is easy. So linear independence do Mn. So proof, and just nothing surprising here. Let me go over it real quick. So I linear independence. So if I have some something like sum of AI d over dxi, where this is some function. Some element from here, AI plus maybe bi, bj, sum over j, d over d theta j. And suppose that I have such a derivation, then really AI is just an application, of course, of v to xi, right? And bj is just an application of v to theta j. And so therefore, if v is 0, then AI and bj is 0. AI bj is 0. So this is really nothing happened here. The fact that it's complete, so completeness. Well, we just form, so suppose that I have some derivation. So this is super derivation. C infinity mn u. Then I would like to see that it is decomposed like that, right? Then, of course, I just take these coefficients. I just define AI to be just v of xi and bj to be v of theta j, and then I form the difference. Let's call it d. It's the difference of v and sum over ai d over dxi and sum over j bj d over d theta j. Then this is derivation, all right? And moreover, it is 0 on all polynomials. So we use our standard, like already standard argument. We use Taylor decomposition argument and the fact that it's this guy is 0 on polynomials, right? So let me fix the degree up to which I will consider my Taylor decomposition, right? So let me fix, in this case, as I have in my notes, I think it's true, I need to fix k, which is greater or equal than n plus 2. Right, and let me fix also some arbitrary x inside u. And then let me consider arbitrary f. So this is just a smooth function, so to say, on u, super function. Right? Then I can decompose f as polynomial p plus r, where p is really a polynomial in x and thetas, right? So this is p polynomial in x and theta, and r is such that its corresponding stock is inside M, the maximal ideal, but in which power? Well, k. Then I apply this d to my f, so this will be dp plus dr. This is 0 because it's 0 on polynomials. And this is, we would like to see that this is 0 at x, right? But since we fixed x arbitrary, this will be the result that we need. But then dr, just because of the Leibniz rule, dr is actually inside x. M x all right, and therefore but I take k greater or equal than n plus 2, right? So this is so therefore this guy is just 0. Is it yes, well, it is. This is not 0. Sorry. This means that dr at x is 0. That's what it means, right? Because the part with theta, this is gone because of the degree, and the part without theta should be 0 because it's in the maximal ideal. Right. So this proves everything. So therefore, df is 0 because x was arbitrary. All right. So next thing I want to discuss is tangent. What is a tangent vector? So definition. So let me fix a supermanifold. B supermanifold. And let me fix, of course, a point in x. Then a tangent vector of x at x is is an element of home. So it's a linear map over R, but it's from OX to my field K. So it doesn't respect right. So that doesn't respect degree as it because I have prime here, but I need to but satisfying the following variant of Leibniz rule. So let me is an element. Let me call it somehow. I don't know, psi. So I need to apply psi. So I'm applying psi to the product of two elements inside OX. So Leibniz rule will say that, okay, it's an application of psi to F times, so here I need to put like tilde, where tilde is, okay, it refers to the notation that we had before, but I will recall it after I finish writing this line. So plus, so this is really an element of K. So plus, what? I need to have f of x tilde times application of xi to gx. So here I need to recall that my notation is that, okay, locally I can write, say, g or f of x as f tilde. Well, locally I can restrict to coordinates, right, where f, so f, well, yeah, so I can restrict to coordinates. Well, f is an element of C infinitum n anyways, right? So in coordinates, it's locally, it has this component without thetas plus sum over I greater or equal than 1 fi theta I. All right? And so this really does not depend on the chart because of locality. And this is well-defined thing, and it belongs to, so if I fix x, this belongs really to K. So we, as I said, we lose all this information because we only, when we evaluate, we really consider this thing. All right. Okay, and so this forms vector space over K, and this vector space we call tangent space. And well, so it's just vector space of tangent vectors at x is tangent space. It's just and it's denoted as usual txx. All right. Now I would like to, so since I have tangent spaces, I can define differential of morphisms. All right. Well, it's also no surprises here. So suppose phi, it's a morphism from supermanifold x to the supermanifold y, the sheaf of structure sheaf of y. So it's morphism of supermanifolds. Yes. Then I can define dxf right, well, I can fix points x in x, y in y, such that phi tilde, well, it's usual differential part of x is y, and then we define the differential dx phi of phi at x as a k linear map. Well, from, of course, tx x to ty y, such that, well, it's defined by the following formula. So d x phi, its value at tangent vector xi. Well, it's just as usual. So this is this can be applied to the stock. So element of the stock at x. So we apply it to some f x, and this will be just application of xi to, well, phi star u. Well, I pull back and then I apply. It's really, so this u here is where this f is defined. So it's inside O. The only thing I need to be careful about is that I have to write y here, right, and x here. And then this now is inside O y of u. So this u is just related to this function that I'm pulling back. So this is definition. All right. Now, well, so we need, let us now prove some theorem, which is like very non-trivial in this case, but it's again the result is not is what you expect. So it is basically what it's called inverse function theorem. So if differential is non-degenerate, then locally your phi is isomorphism. So let's prove this theorem. So let phi again be morphism from x to y. So it's morphism well, of supermanifolds, well, such that, well, and then the following condition. So suppose that for some x from x, dx phi is linear isomorphism. Then okay, let me see how can I. So then actually I can choose some neighborhood V. There exists neighborhood V. This is inside Y, and it contains point Y, which is the value of x under phi tilde. All right. Such that for u, which is phi tilde inverse of v. So this is inside y, this one is inside x. Well, phi, the restriction of phi to u, right? So now this is from u to v. So this guy is just a restriction, right? This of the shift of x to u to v over v is an isomorphism. Well, restriction, I think it's clear what it is, right? No. Да, да, но да, просто самим собой не связанным чем-то, да? Сейчас. Ну, да, надо не прообраз брать, правильно. То есть надо брать, вы правы, еще у, как бы. У из x, и у открыто и содержит x. Да? Да, прообраз не очень. Ну и такое, что понятно, фи. Ну, все, дальше я уже здесь сказал, что это изоморфизм, и поэтому фи от у, фи с волной от у это v. Okay. Fair enough. So okay, let's prove this. So I need to be a little bit more explicit. So what could be a matrix? Like what is the base? Like I would like to see some matrix for dx phi in some basis. All right. And basis, again, this is very natural basis. Well, so first of all, I can just, this is all local, right? So it's enough to prove for x just u tilde mn, and y is just v tilde mn, right? And okay, we don't know for sure if it's, so maybe we have to write LK here. Well, of course, we'll follow that M should be equal to L and equal to K, but okay, we just have different kind of supermanifolds, and we don't know yet that they are of the same superdimension. And okay, so then I have global coordinates on them, and let me have x1 blah 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 xn theta. So here m theta 1 theta n. So these are global, well, just coordinates on x, and with primes, do I want with primes or? Yes, okay, let it be with primes. x1 prime, xl prime, and theta 1 prime, theta k prime. So these are coordinates on y. So once I have coordinates, I have actually basis, natural basis for Tx, for tangent spaces, which is our d over dx i's, and d over theta i's, but well, kind of specified to a point, but what does that mean? It means that we lose some information. So I have d over dxi x is my fixed point, and d over d theta I. So far it's just a notation for some basis of tx for elements of some basis that I'm going to describe now what it is. So d over dxi x should be applied to an element of a stock, say fx. So I'm applying it as follows. I'm just taking f, so this is my function, and then I apply d over dxi to it, and then I should take, so this still will contain some thetas. So then I get rid of thetas and evaluate at x. So that's what I'm doing. So I'm getting rid of thetas. Well, this is the same as saying that it's just df tilde over dxi, right, of x. Just the same thing. Now, what about d over d theta I? Well, basically it's just the same thing. X is the same thing. But in this case it's just not equal to this one. So I really need to apply d over d theta I to this guy, and then take tilde of x. Right. Maybe tilde over the whole thing or whatever. But tilde means that I'm looking for a term without thetas. Right. So this is okay. This is a basis, and I guess one should prove it using the same argument, like Taylor expansion and the fact that it coincides on or maybe you can deduce it from the previous. I don't know. But okay, this is a basis, and so I would like to see how d phi looks like in this basis. So okay, let's see. So I can take dx phi and apply it to d over dxi x. And then I am applying this to some function. For some reason it's now g here. Okay, so let's keep it consistent with my notes. But yeah, so g should be local at y. All right. So what does it mean? It means that I am applying d over dxi x to phi star. Let me not specify the open subset. G leaves gx, right? But then this is just application of d over, by definition, d over dxi of phi star g tilde, right? Well, at x. So at x, that's what it is, right? Then this equals to. So now I'm using locality of phi, and so this is just composition really. It's just G tilde component of G, well, precomposed with phi. G tilde, phi tilde. Предлагаю вам прослушать патриотическую информацию. Я не удивлюсь, если сейчас что-нибудь такое будет. Ага.
Вот d по dx и вот эта вот строчка, где равно чему-то соловной, почему там нет d?
Вот здесь? А потому что волна это значит. Ну, влево ее нет, ну, как бы, это просто, вот здесь, просто по определению, я хочу, чтобы вот этот был касательный вектор. Это просто, как бы, это определение d по dx этого. Да, у нас было по определению, как бы, вот без индекса, как он действует просто на функции, как в векторном поле. Ну вот как, это мы не определили, а что это значит. Вот я говорю, что вот просто вот этот символ, это касательный вектор, который я определяю вот таким образом. Там уже от этого ничего не должно зависеть, это просто должен быть элемент поля. Да. Ну да. Хорошо. Okay. So let's continue. Yes. Okay. So I have this. So I need to be. So I need this. Right. So this is just, you know. Then I use just a chain rule, really. Right. So this will be sum d g tilde over dx. This is just, you know, multivariable calculus now. G prime times d. So phi. So phi actually sends. Well, phi what? Phi is from here to here, and phi sends x prime to something inside here, right? And phi tilde sends phi to just, well, it's just a function in x, really. Okay? So, so phi tilde, it's a function in x. Phi tilde, so I need some index here, j. It means, so phi tilde j is just phi applied to x prime j, and then taking tilde. All right? So this thing, and then I need to differentiate with respect to xi. This, because this is really a function in xi. Now this is just chain rule. Right, but I need to take this at point, then at point x, right? Well, x is somewhere missing everywhere here. And so this, but this guy is in the point y. That's how chain rule works. Now then, this is just this matrix d phi tilde j over dxi, right? And then I need to, so what is this guy? This guy really is an application of d dx, where am I? So it's just application of d over dxj prime to g, to the stock of g at y, right? And this one is at x. And I have also sum over j. And this, and I also have to put here y. So now I think I didn't miss anything. Only subscripts. Anyways, my goal is, so I am applying dx phi, and writing this down is as a, the linear combination of d over dx primes. And here's the matrix that it should be multiplied to y. What about d over d thetas? What does it do with that? Right, so dx phi, I need to apply to d over d theta I of x. Well, again, this applied to gy. By definition, I need to apply phi star to g, then take derivative with respect to theta I, and then take tilde of that and evaluate this at x. All right. Now I need to see, so okay, my g looks as follows. It is just g tilde plus sum over I from 1 to, by the way, g lives in y, so to k with some coefficients, gi theta I prime. And then plus, this is just an introduction of this coefficients, that just like a notation, which stays in front of theta I primes. Then I also have some gi's theta I, where I is greater or equal than, the size of I is greater or equal than 2. All right. So what I need is just notation for this, guys. Phi star of g, the one that I'm looking at here. It's what? Well, it's just g tilde phi tilde, right? Plus sum of 1 to k, and then I just need to precompose g with phi tilde, and then have theta сейчас, вот эта функция, да, но я должен, сейчас, одну секунду, то есть, сейчас, еще раз, чего вы говорите? Да, g это функция, но Да, тет нету в GI, правильно, но это просто как бы умножение, да. А здесь я должен написать просто тета и т. Сейчас, одну секунду. Вот это просто функция. То есть что я пишу? Я пишу коэффициент, который просто функция. Да, g без волны, это я согласен. Совершенно верно. Да, g это без волны. Дальше мне нужны какие-то коэффициенты, которые я сейчас определю. Там, so I'll write f, I, j, theta, some theta j here. And so here I also will have sum over j from 1 to, so how many j's I have? I have n j's. Right? And then plus something that I don't care about, so this is so this will be not g, but rather something else. Ci theta. So by the way, here I have theta primes, and here I have without theta, and here I is greater or equal than 2. So where well, it's clear what are phi ij. So I'm applying phi star to theta and look for a linear term in there, right? So I apply phi star to theta I, and I need to write down. So it's sum over j phi ij theta j. J is from 1 to n. Plus terms of higher degree. By the way, they should start with degree 3 in thetas, right? So this should be odd. So the result should be odd, right? So therefore, that's why, by the way, I don't have like a constant term here, right? So some phi I j k l theta j theta k theta l, and so on. All right. So these are my phi ij's that I'm used here. В левой части штрих, правильно, да. Right. So therefore I can continue. So I am computing this, right? So I can continue. And so I have this, right? So I differentiate with respect to thetas, right? And then take tilde. So therefore I should get rid of everything which still contains theta after differentiating with respect to thetas. So the only thing that will be left is this term. So I will have sum over I and j. I think I'm not messing up the order of indices, but if I am, let me know. Phi ji, g, j composed with phi tilde. And then also, well, the summation over I from 1 to k and j from 1. By the way, sorry, is this true? No, the summation over I don't have summation over I. Yes, so summation over j only from 1 to n. So that's it. Right. But I am just saying that this is really sum f over j, f, j, I, d over d theta j prime applied to g, y. So I'm just saying that this guy is exactly the result of application theta d over d theta prime j prime to g. And let's see. So g is like that, and indeed I will get g j, and then this is at really, so this phi tilde means that I have to take this at y. So here it was at x, right? So now it's at y, and this is just number, right? Which is just this number. Okay, so now I'm done computing my matrix corresponding to phi, because theta is expressed in terms of theta prime like that, and x is expressed in terms of d over dx expressed in terms of d over dx prime like that. So I can now write this in the matrix form, d phi, I mean. And this will be handy for future use, anyways, what we did right now. So dx phi has the following block structure. I have 0 here, 0 here, and then something that I can denote by d phi tilde over dx here, and something that I will denote by phi here, where phi is really maybe let me rather put here phi transposed, because I really want phi to be phi ij, this one. Because here I have transposed, but I really want this to be in this order, my indexes. All right. Okay. So, anyways, we know, by the condition theorem, this is inversible, right? So therefore, blocks are inversible, right? So therefore, we have d phi tilde over dx, and phi doesn't really matter, transpose or not, these are invertible. In particular, phi tilde is diffeomorphism from, well, I am saying diffeomorphism, it means that I have to have like a just usual smooth structure on my supermanifold. We never discussed it, but we do have it. Right, it's given by, by local chars, and in local chars you need to look at, tilde part of the chars, and this will give you a smooth structure. So that's why I can say diffeomorphism. So this is diffeo from some neighborhood u of x to some neighborhood y of v of y, right? And we can assume that both of these things, so these are some functions, right, on which depend on x, right? And so when we shift x a little bit, inversibility of this still holds true. So we can assume that u and v are small enough such that such that d phi tilde over dx and phi, these are inversible for all x inside U. So can assume that well, d phi tilde over dx and phi inversible for any, okay, x is fixed point, so how do I, t inside U. Let's call it like that. Okay, so now I'm defining not like a complete inverse, but as much as I can do for now. So I define the let's call it psi. So this goes backwards naturally. So we have, it's from V. By the way, we have tildes, right, from, okay, from V. So from V, K, L. By the way, at this point, we already can say that K equals to M and L equals to N, right? Because this is an isomorphism, right? So therefore, it should be square matrix at least, right? So this is Mn, this is U Mn. So how do we define it? As follows. Well, we need psi tilde, which is homeomorphism. This is really, let us put it, phi tilde, well, restricted to V inverse. Well, restricted to U inverse. So this is one. Now I need to define also pullbacks. I need to define pullbacks. So psi, and as we know, I can define pullbacks only on xi theta j's, right? So that we proved, and this defines the pullback, well, the morphism for us completely. So we have psi. We'll define psi star of x. Sorry. So it goes from U. So it is coordinates on U, right? Because it's pullback. So without primes here, then, right? And I just define this to be really, phi tilde inverse the ith component in coordinates x prime, right? So this is ith component in coordinates x prime, right? And then psi star applied to theta j, or even let me do it in matrix form rather. So let me write the whole vector. So this is equal to phi inverse. So we only invert like using just linear term. So it's not a completely inverse. So phi inverse of theta 1 prime, theta n prime. Okay. Then, well, we can, of course, we can compose. So first apply, for example, psi star, and then apply our original phi star. And then, okay, let's call this tau. So this is not identity, but this is almost an identity. So it's identity. So how to plus something? Okay, let me call it m. This m has the following properties. Maybe let me write it here. So okay, let J be ideal generated by theta. Right, so I'm going by psi from theta to theta prime, then from theta prime to theta. So really, I need to generate by theta, not by theta prime. Right. Then I claim that m of xi is inside J, and m of theta J is inside actually J cube. Because, so what did I do? So for example, this J cube. So I first apply psi star, which is taking theta primes and considering phi inverse. Then I'm applying phi star, which actually works like that. So this term is just theta I again. So this is my identity. And then plus m, and m already should be of the term of start with a cubic term. All right. And this is the same kind of discussion. So I'm really caring that it would be an identity on just the first term, which is xi. By the way, I can even put, so this is still true, but I think I can even put square here. Can I? I think I can. Right. Yes, because the next term should be even, right? So it should consist of two thetas. So this guy is. Wait, sorry. Yes, that's true. Okay. So all right. But so what our goal? Well, our goal is to see that this is nilpotent. Then it's almost true, because then we found right inverse. But then, well, you can, there are a couple of steps to see that it is left inverse as well. So I would like to see that this guy is nilpotent. Well, of course, I can try, to use this argument that J to some power is 0, but it's not like if. So the problem here is that M is not homomorphism, right? So this is homomorphism, but if I take like identity plus something, this is not homomorphism of rings, right? So I cannot apply M many times and raise this power. Right, so I need really to be a little bit more careful. Let me see. So, how do I proceed? So let me fix some I, which is I1, I2, consists of R indices. So this is each I. K, well, IS is between 1 and n, and they are all different, by the way, also. All right, but then I'm applying tau to theta I. What do I see? I see that it is theta I1 plus something, let's call it beta I1, theta I2 plus something, call it beta I2, and so on. So the last term will be beta IR, theta IR plus beta IR. Each beta is inside J3, right? So let me write this down. So this is inside J3. This is inside J3. So I claim that actually the result is then inside JR plus 2. Sorry. It's not like that. No, sorry. This is the result is the following: is theta I, so identity, plus something inside. So let me write JR plus 2. Okay. So it's identity plus something inside. So tau is identity plus something inside, which sits inside R2. If I substitute theta to the power I into it. Okay. So this means what for M? This means what for M? For M, it means, right, so if now I take G to be something like H theta I, where this guy is inside just C infinity of whatever U, then if I apply tau to my G, so this will be what? So this will be H plus some W times theta I plus some Xi. Well, H is this H, theta I is this theta I, right? Well, I'm just using that this is homomorphism. But this guy, as we agreed, is inside J squared. This is inside J, and this is inside J R. Well, this is inside JR, right? And this is inside JR plus 2, even, right? So this is actually G again plus something. Again, let me use it like that. Something inside J, but in which power? I think J R plus 2 already. All right. So therefore, if I take something, so if G is inside JR, then tau of G is inside G plus JR plus 2. All right. So this actually shows that M of JR is inside JR plus 2. All right. But then we can, so we just need to notice that M of just G to the power 0, right, which is C infinity M N of U, is inside J, should be inside J. Well, it's just because of this. It's inside J square even, doesn't really matter. So therefore, m to the power sufficient, or I don't know which one should we take. I think n minus 1, n will do, right, is 0. Well, in particular, it means that 1 plus m is invertible. And this means that psi is really right inverse for phi. So psi is right inverse for phi. But why is it left inverse? Is right inverse for phi. Well, we just need to use chain rule, which is we didn't state it, but it is true. So basically, if I have a composition of morphisms, that the corresponding differential is just a composition of differentials. This is proved, in straightforward way. Nothing interesting. Let's not spend any time on that. Пси правый обратный. Ну, как я могу взять вот это, он и правый, он может быть, значит, у него есть и правый, и левый обратный. Ну, в смысле, он и есть. Как бы. Давайте я домножу на вот это в минус первый. Правильно? Справа. У меня получается фи со звездой, пси со звездой на единичка плюс m минус первый. Равняется единичке. Ну да, значит, обратимость со звездочкой. Ну, в том смысле, что на каждом этом открытом пространстве у меня pullback. Значит, ну что, мне нужно действительно что? Что у меня пси с волной – это обратный, да, к фи с волной. Но это как бы я руками положил. Ну и что все морфизмы тоже для всех, ну, пулбеки для пси со звездочкой, они обратные для всех пулбеков фи со звездочкой. Да, мы подкручиваем для пси, да. Да, правильно. Значит, что нужно заметить, видимо, что m с волной это просто 0. Ну как я беру m, как бы, и он у меня уже будет лежать и в J, и в J в кубе. Вот. И поэтому он никак не трогает то, что пси как бы с волной обратный к фи с волной. Да, это правильное замечание, да. То есть эта подкрутка нам не портит то, что уже было хорошо. Окей. So now we need to finish, but we're almost there. So now I just can take the composition, right, which is identity morphism. Consider its differential. So I take psi phi. Well, psi times well this should be like, I don't know, psi. Not tilde is bad. So okay, let's call it eta. So eta tilde is psi tilde, and eta star is just psi star times 1 plus m star. All right. So we know that this is actually identity, right? So I can take differential, use chain rule that we didn't prove, but I am claiming that it's just we do have it, and straightforward check. So it's still identity. Therefore, d eta is invertible. Well, it's actually well, d phi was, so d eta is inverse to d phi, right? So actually it's an isomorphism as well, right? So d eta is isomorphism. So therefore, eta will just repeat everything, and so eta has right inverse. I don't know, let's call it eta prime. Right? So let me see. So I have phi eta, and then eta prime, it is phi, right? On one hand. On the other hand, I can so but phi eta is just identity. Well, here I use that eta prime is right inverse to eta. But then I can use that eta is right inverse to phi. So therefore, this is just eta prime. So actually, phi is eta prime. Prime. In particular, it means that if I multiply eta by phi from the right, I still get an identity. And we okay. So we proved the theorem, and you see it's not as simple. So the statement is simple and expectable, but the proof, you need to go technical. Well, at least we see how to work with all that stuff, and also we computed, just to know that we computed the matrix for d phi. We will use it from time to time. Okay, so that's finish today.